So pretty soon we're going to be done with the logic section, and we're going to start with our first axiom. And it's this, axiom 1. X equals X. This is a proposition. Every axiom or theorem or definition that we look at will be in the form of a proposition. And since this one is an axiom, it's sort of one of our starting points. It's one of the propositions that we accept as something you can start with for the purpose of further deductions. Now, what I want you to notice is that in this statement, in this proposition, it looks like X is free. It's not bound. So if I were to write this if I were to express what this is saying in English, I would say X equals X. I cannot say that without mentioning X. The X here is free. In this proposition, the X is free. So this seems to be about X specifically. But, okay, so the way people would traditionally interpret this axiom is they would say things equal themselves. It's an axiom about equality, which is saying that everything should equal itself. Well, that sounds more like for all X, X equals X. That's everything equals itself. So how come the axiom is written like this, X equals X? Well, there's an implicit, unspoken universal quantifier. And in this video, I just want to explain why it's still correct to omit that universal quantifier and why people omit it. So first, why is it still correct? Well, if you have this axiom, so we accept that the proposition X equals X is true, then we are accepting that it's true without any outside assumptions, right? It is just true that X equals X. It is simply true. We don't need to assume X is a flower. We don't need to assume it's green or anything about it. Well, then we have a one-line proof, there it is, that X equals X without any outside assumptions. So if I just stick some words around it, consider any X, then X equals X, then here is a perfectly valid UG, universal generalization, type argument for this. Everything equals itself. So since the axiom says X equals X without requiring any external assumptions about X, it's just a standalone statement that we accept as true, we can generalize and say, okay, this is actually saying everything equals itself. And that is why the universal quantifier could be tacked on, and if it's omitted, then you can always put it on. It's because you're just one UG, one universal generalization argument away from just putting it on. Now, why do people omit it? Why do people leave it out? Why not make this be axiom 1? Wouldn't that be more clear? The answer is basically laziness. If we can write less, if we can get away with writing less, then why not? So people will write this, but they will know that they're just a universal generalization away from putting the universal quantifier there. And one thing to notice also is once you've got the universal quantifier there, then you can, from this statement, which is deduced from axiom 1, you can use universal instantiation to now apply this to any particular thing. So you can deduce from this, using universal instantiation, that the proposition X equals X is true when you replace X by any term that you want. Any term that you want. So let me show you what I'm using for this. So I'm just doing a universal instantiation, which says if I know for all X phi holds, then I can deduce phi, but in fact I can deduce phi with the X, whatever variable was quantified here, replaced by any term that I want. So, for example, I could deduce 3 equals 3, or 1 plus 2 equals 1 plus 2, whatever plus means. So even without knowing what it means, I can deduce at least this fact about it from axiom 1. Yeah, so this idea that starting from a standalone statement that might be part of an axiom or a theorem, you can do a UG to throw on the previously implicit universal quantifier, and then you can do a UI to replace what was originally free variable by some other terms. This idea I have sort of packaged into one rule, which I will show you. It is derived rule 31 here, which I'm calling variable substitution. So if you have a proposition like x equals x, given it, meaning you know it's true, if x is arbitrary, for example, if it's part of an axiom where there's no external assumptions, or if it's part of a theorem where it's just a standalone theorem, this is true, then you can replace the free variable x by any term you want. So let me give you an example from much later. So let me just pick a random theorem, regardless of whether we understand what we're looking at or not. I can just pick a random theorem here, like, how about this one? Theorem 20. This has two free variables in it. Or actually, how about this one? Just to pick something that's a little bit more complicated looking. So this has two free variables in it, x and s. So here's theorem 19. It has two free variables in it, x and s. And it's a theorem, meaning it's a standalone thing that's true. So if you look here, it has a proof. You know, the proof begins and ends, and then that's it. This statement here is just true. The free variables x and s, according to the idea that we just discussed, or that derived rule 31, which says that you can UG to put on the previously implicit universal quantifier, and then you can UI instantiate to apply it to a specific case. Using this idea, here are some consequences of theorem 19. And actually, first, let me explain the reason why this idea of derived rule 31 works. Is that from theorem 19, we can deduce this, which is, you know, I didn't say this in lecture, but you saw it in the reading, that this comma-separated list means I've got two nested universal quantifiers for all x, for all s. Then from theorem 19, we can throw in the implicit, using universal generalization, we can throw in the previously implicit universal quantifier. Then we can instantiate and apply to specific examples of x and s and get some consequences, like, for example, 3 in 1, if and only if, you know, I'm just copying and then just replacing the x's by 3 and replacing the s's by 1. And this might look like nonsense if you knew what the symbols meant, but it doesn't matter. It's true if theorem 19 is really true. Another consequence is 1 plus 5 you know, things like that. And regardless of whether you know what these symbols mean, you should agree with this, as long as I tell you that these stand for terms, and we will learn what they mean later. But that's it. This is a term, so it can replace s. And so is this. This is a term, so it can replace x.